Welcome to today's webinar. Why code optimization is the next frontier for FinOps. We've got a very practical session lined up here today. I've got Mike and Craig talking. I'll introduce them in a second, but we're going to focus less on theory, more this is what code optimization looks like in your code and in your bill. That's the vibe we're going for. Before we dive in, I'm Ashan. I'm the head of growth at Frugal. Frugal is a cost engineering platform that helps FinOps and engineering teams find and fix cloud waste that doesn't generally show up until it's already in your bill. I'm joined by two of our co-founders. We've got Mike, our CEO. The thing about Mike is he loves starting companies, and he's pretty good at it, I would say. He's founded 4 companies and sold them. They're all venture backed, including Watchfire to IBM and Blaze to Akamai. So Mike is also an active seed investor and board member across a bunch of startups. We also have Craig, who brings the technical chops to Frugal. He is the mastermind behind the product. And before joining us, Craig led cloud platform, SRE, FinOps, engineering at Sneak, and was a distinguished engineer for Elastic Observability, which is super cool. So between the two of them, you're in great hands. Honestly, they've seen every flavor of the cloud cost problem. And yeah, you're in good hands. We'll walk you through the agenda real quickly. So we've got, like I said, a practical session. It's tightly structured, but we'll have plenty of time for Q&A at the end. We'll start with some context on how FinOps has evolved and why the old playbook is kind of running out of road. Then we'll get into the meat of it, why code is increasingly the primary driver of cloud costs and what you can actually do about it. We'll walk through some real code examples with before and after cost numbers, and then we'll open up for some questions.
Thanks, Ashan. Hey, everybody. Again, Mike Wider, co-founder and CEO here. Happy to be here and excited to talk about code optimization. So maybe just before we get into it, just to set the stage, probably everybody's familiar with this, but I'll kind of go over it. When we think about our cloud spend, it's really kind of a function of two things. One is what's the rate we're paying for something and how much usage we have. And so in terms of optimization strategies, most companies have tried to optimize the rate they pay through committed use discounts, reserved instances, saving plans, stuff like that. And most of the cost avoidance or usage reduction has been principally focused on workload optimization, which is the sort of fancy word for trying to find underutilized servers or servers that nobody's using at all, and trying to get rid of that. And all those things make a ton of sense. Obviously, you want to reduce your rates, you want to reduce, underutilized servers. But increasingly, what we're going to talk about today is something else. It's really about code optimization and why that is becoming a bigger and bigger driver for opportunity. But it's also maybe something that not a lot of people have focused on in the past. And there's a lot of potential upside to leverage there. 20 years ago, almost to the day, I think it was March 2006, Amazon launched AWS. And that sort of ushered in the cloud era. And the two first products that they had there were EC2 and S3. And so initially, most people were taking workloads that were maybe running in their private data centers and moving those to the cloud and taking advantage of the fact that they didn't have to run a bunch of servers. But it was sort of what they call the lift and shift era. And then, we evolved a little bit in the sense that people started to get innovative and say, hey, instead of just moving a workload that was in my private data center to the cloud, we're going to start creating cloud native apps. And as we did, we saw that what the usage costs, in the first era were mostly about infrastructure. EC2 was kind of dominant, or the VMs. And when we got into cloud native applications, we saw these usage costs begin to grow. And so we started leveraging all sorts of other managed databases, observability tools, Datadog, and all these things. So there's now, in Amazon alone, these 2 products have evolved into over 200 products that Amazon has that are available for you to take advantage of. And then the third area that maybe we're entering now is what we call the AI native era, where the usage costs have now gone from 20% in era 1 to 80% for a lot of cloud native companies. And that's principally, as you guessed it, because of tokens and the rising costs of AI for companies that have adopted AI in a big way. And so when we're talking about code optimization, really it's really looking at a lot of these usage-based costs and understanding kind of how we can optimize them. And so when you look at workload optimization is principally about the host infrastructure, but code optimization can help you with infrastructure, but it also is probably the only thing that's going to help you with things like serverless, with AI, with storage, caching, observability, messaging, and on, all these other things where developers are adding some call out to an API or request a third party service, maybe that you're paying by the consumption of bytes, the consumption of tokens, the consumption of requests or log storage or some variable metric that is you basically your code is spending money. And so in workload optimization is really billed by the time where I have a server and I'm charged X dollars per hour or per month or something like that. In the code, it's really about the usage of a given service type. And so that's kind of be the focus of what we're getting into today, which is how to address those things. The first kind of maybe challenge and observation here is that today a lot of cost optimization work that people do is reactive in the sense that developers write code. They are often, it's not clear what the costs are of those things. We deploy those to the cloud, and then sometime later we get the bill back. And this is a challenge for developers, and this for cost optimization, principally because number one, pre-deployment, they don't have a lot of visibility about what these costs are. So they may be adding some code or a feature that utilizes some of these services in some way. And it's not always easy to know how that's going to change the cost dynamics of my application until later we get these bills post deployment. But by then, developers have kind of moved on to other things, and they have a million other projects that they're working on, and it's always super hard to kind of go back and get developer attention on something that they've already moved on from. And so as such, a lot of these costs really don't get optimized or dealt with. And so we've seen this problem before. Both Craig and I we worked in the past in the area of security and performance optimization, where we used to do a very similar thing where, security used to happen very late in the cycle. Developers would write code, they would pass it on to some pen testers or infosec team that would look at the application, tell them what's broken, and kick those issues back, repeat that cycle until we had cleaned up all the problems. And the reason is that it's just way cheaper and easier, but also, developers, while I'm in that code, fixing a problem is way easier than getting me to come back later and look at it. And so what we're going to talk about today a lot about is also shifting left cost. And I think it's pretty obvious that in the future, we will all look at cost as we write code, as we build systems versus how we do it today, which is kind of in arrears. And we're going to talk to you today a little bit about, how to make that happen. So principally speaking, there are kind of three places that we see you can place code optimization. Number one is in the IDE, or maybe a better term in Claude or in a console that your cursor where you're building code, and you want feedback as you write the code to understand what are the cost implications of this new code that we're creating. Then the code has kind of come together. We're in GitHub about to do a pull request, and there's often reviews for quality for other issues. We want to look at now that whole piece of code is together, look at it for cost issues and understand the cost implications of that. And then lastly, in production, and then we want to continually analyze the production code and applications to look at costs on a continuous basis. So kind of thinking about it from a person's, a human or AI standpoint, for the Claudes of the world, we want to help them write the most efficient code possible. Or if it's if it's an agent that's building your using agents to build your code, we want them to create efficient code by default. As a developer, I want to understand how can I optimize the cost of any new features I'm creating, or what's the cost of a new PR that I've just created. And if I'm a FinOps person, I might want to know how can I cut our Datadog bill. So different personas maybe have different needs for code optimization, and we'll talk a little bit about that. But here's an example maybe of a pull request. I'm in GitHub, and what you want is that if a developer has introduced a feature that has cost implications, that this, you have some gates or systems or guardrails that will flag that and say, hey, it looks like, Mike, you're about to add some code that's going to have a significant cost change. Make me aware of that. And then also provide some recommendations as to how I might reduce that cost. And so today, these things are invisible. And what we want to do is try and make them visible to the developer without interrupting their workflow, without saddling them with too much, slowing them down, but provide some level of cost visibility as we create code. Number one is that I might have missed something in that I made that recommendation, but the developer ignored it, or it was just missed in some way. Second, though, is that the application usage pattern may have changed. And so what made sense for how I created something, say 6 months ago, might have made the most cost efficient decision. But now the usage has changed. And so we need to reevaluate how we are using that service, and are there more efficient options available? And maybe a third reason could be that there's just a better option now in terms of new technology. And so, for example, there's a better model that produces the exact same output or benefits, but it's way, way cheaper per token. So those are just a few examples. One thing, that's important from a reporting standpoint is that with FinOps today, it's mostly about, what are the costs? What am I paying? Maybe how that breaks down if I've got good tagging by product. What developers need is not, though, that high level data. They need low level data, right? I need to understand, the costs at a much more granular level. And so what you really want to do is break it down to the component or service or even line of code, and to identify, waste in the code or how it's been implemented in terms of recommendations for how those services can be made more efficient. And that's exactly what Craig is going to walk you through, is to get technical now and kind of get in the weeds and talk a little bit about some very specific examples of very common usage-based costs that people might be using, and how code optimization can be used to optimize that cost without impacting the actual functionality that's delivered to customers. So Craig, over to you.
Thank you, Mike. So with services where you're paying by the usage, you can fall into a pitfall where you're sort of paying more than you need to get the value that your application requires. So we call that cost trap, sort of accidental overspending. And to kind of make that a bit more concrete, what I was going to do is just walk through a few examples of code that is spending money on managed services that have a usage-based cost, and show you how they can end up spending more than they need to deliver the value to your application that they are meant to deliver. So a cost trap is not necessarily bad code. It may be just code that started reasonable. It's code that works. It's doing the thing that it was meant to do, passes review, and so it ships. But then things change. Your usage of your system scales up. You're getting more requests, more users. The data that you're processing grows. Maybe there are new capabilities added to the managed service that you're using that you don't get to take advantage of unless you change your code to use them. So things change, and the trouble is that because your application just keeps working, and because you're focused on new things, often, these costs just accumulate, and you end up with these problems growing in parts of your code that are still working fine, but are now inefficient. And so to try to just make this concrete for you all, I've got 3 examples I wanted to show: one for S3 usage, one for OpenAI usage, and one for Datadog usage. They're just meant to show how good code can kind of go bad, and what we can do to find those issues and fix them. So the first one here is S3. So we have our application is using S3 to store product usage events as customers of our product use it, and it's writing those out as JSON objects into S3. So that's a piece of text that stores the data. So our usage of our application has grown, and we're now up to 100 million events per month of things that we're storing to S3, and they're about 5 kilobytes in size each. So here's our original code to do this. It's this one function, record event, that takes in the user event as a parameter. And all it's doing is writing that, it's taking that user event, turning it into a JSON string, and storing that to S3. Now, when you use S3, you pay for, there's multiple different parts to what you pay, but one part is the storage. So this usage of S3 is now storing 500 gigabytes of data. So that's costing $115 per month. But the more significant cost is actually the put requests. So with S3, you do pay every time that you talk to S3, either to write something or to read something. So we're doing that a lot. We're calling this 100 million times per month. So that's costing us $500 per month in just calls to the S3 API. So let's tackle each of those costs and see if we can keep the same functionality in the application and still use S3, but pay far less. So the first thing we'll tackle is this storage cost at 500 gigabytes. So a really simple thing that we can do, this is some text data that responds really well to being compressed. So with just a couple of small changes in the code, we can add gzip compression to take that, the size of the data that we're storing to S3 down by 75%. So now with that change to gzip the data before we send it to S3, we've reduced our storage costs down to about $27 a month from over 100. Okay, so that's a good start, but we really haven't tackled the biggest problem yet, which is the number of put requests. And I think Scott Meyer's already got the right idea. What we want to do here is batch these. So these, instead of sending each one of these requests independently, this data responds well to being buffered and batched up into one thing that we can send in a bundle to S3. That will reduce 99 out of 100 requests to S3 and cut that cost down by 99%. So by combining these things together, we start out with something that was costing us, that one function was costing us $7,380 per year. By applying gzip to make our object smaller, we got it down to 6,324. And then by attacking that API cost, we were able to really bring it down to $384 per year. So for this case, for S3, here's some interventions we can take to really reduce the cost. Let's take a look at another example where we're looking at OpenAI. With OpenAI in this application, we're using it to classify customer feedback comments by sentiment. So is it a positive comment, a neutral, or a negative comment? Our application's been doing well. We're up to 500,000 comments per month at this point. When this function was implemented some months ago, it was implemented using GPT-4o. So let's revisit this code and see if we can make it more efficient. At the moment, so this function, classify sentiment, gets the customer's sentiment comment as its input, and it opens up a connection to OpenAI, specifies that we're going to use a GPT-4o model, and sends a prompt that asks for a classification as positive, negative, or neutral. When we look at the cost that this is driving, with OpenAI, there's really sort of two types of costs. There's input token costs and output token costs. So with this one, we're spending $1,125 per month on input tokens and $750 per month on output tokens. So let's go tackle all of those costs as well. The first thing that I sort of see right away in this one is that there's something kind of wrong with our prompt. We have this date time now very early in the prompt, and that is going to break a feature that OpenAI built to help reduce cost. They have a feature called prompt caching, which if your prompt is static for the first part of the prompt, all those tokens become cached tokens, and you pay far less for them than a regular input token. Unfortunately, because we had that variable date right at the beginning of our prompt, it was breaking that OpenAI capability. So we don't want that. We can very easily reorganize our prompt a little bit so that we can take advantage of prompt caching. So just by sort of changing the ordering of how we construct our prompts, we have now influenced our input token cost significantly. So we're now paying $438 for our cached input tokens and $250 for uncached input tokens. Those two things add up to what, $650 or so. 600, a little under $700. That's a lot better than the 1,100 we were paying on input tokens before. Okay, so that's something about the input tokens. Now let's tackle this output token cost. What we can do here is use structured output. So I don't know if you've ever had the experience where you ask ChatGPT a question and you get a longer answer than you really wanted. That's what's happening here in this application. It was saying, I want it to be positive, negative, or neutral, and explain your reasoning. I think the original prompt was. That's totally unnecessary inside an application where all it's going to do is parse the output and store it as positive, negative, or neutral. So what we are doing with this optimization is just being specific with OpenAI that we only want the output to be positive, negative, or neutral. So with a little bit of more usage of OpenAI, we can specify that's the format we want for the response and reduce the output tokens significantly down to just $75 a month. Okay, this is all good. We've done something about the input tokens, something about the output tokens. The other thing, though, is that we've had drift. Like this was written several months ago when maybe GPT-4o was a good choice. But now we have much better options. So for a classification task like this, GPT-5 Nano is a really good choice that costs a lot less. So we can get just as good a performance out of something that is way less expensive. So by just making one more small change in the code to go from GPT-4o to GPT-5 Nano, we can really drive down the cost even further. So we went from originally paying $22,500 per year for this one classification function down to $17,250 by getting prompt caching working as it's intended. Then by being specific about what type of output we wanted, we could further reduce that to $91.50. And then by realizing that for the task, there was a more appropriate model now available, we could drive that down even further. Okay, one more, Datadog logging. So here's a case where we have multiple verbose log statements in a single method. That method is getting called now 16.7 million times per month. And it's logging 3 log messages each time. So that's 50 million log messages. So with Datadog, you pay by the number of messages and also the number of bytes. So in our method, we have a process order function. At the beginning, it logs 1 log message with a bunch of information. Somewhere in the middle of that same function, it logs another message and a third one at the very end. These are all kind of in the main line of the function. So the math isn't too complicated. Instead of logging 3 messages, if we could reduce that to 1 message, that would be better. And so we can take this down to 1 message and also reduce the verbosity of what we're logging. We can still keep the key information that we need for debugging, but just reduce the amount of extra text we're sending. By reducing the amount of text, we reduce our ingestion cost. And the most important part is we reduce the number of log events by by 2/3. So a small change in one function that was, causing one function that was causing $1,000 a year of Datadog logging costs and brought that down to just over $300. So these are all some examples that we use to sort of help you see how cost drives directly from code. All of the code examples we looked at worked fine before we made our changes, but it didn't mean that they were efficient. To get to the cost, you need to look at the bill, and all of these usage-based services can have complicated billing models. So it's important to understand which components of the bill are the real cost drivers, because that's going to guide you to what needs to be optimized. Often it's not a big change. So just a few lines of code made a huge difference in the cost of these functions. And nothing is static. So just because something is efficient today, as your system, as load on your system changes, as new capabilities emerge, it may not be efficient tomorrow. So you have to kind of keep up with this stuff as you go. Anyway, just an example that could show you that a few small changes could make a real difference in cost in just a few parts of your code. And it doesn't take very many of these cost traps to be hidden to really drive your entire cloud bill.